Okay, so it's our pleasure to have Paolo Pani from Roma, via Roma. From Sapienza, he'll be telling us about Hawking evaporation in gravity theories with higher curvature terms.
Okay, thank you very much. Thank you for being here. Thanks to the organizers. It's a pleasure to be here in person. As you can see from the title of my presentation, I'm not going to talk about fuzzballs, unfortunately, today, but hopefully the topic will be sufficiently interesting for this audience. And I'm going to present some very recent work. Is these two papers here? Sorry, I think I'm not able to use this pointer. Anyway, yeah, it's these two papers here. Done in collaboration with these people here. So it's Fabrizio Corelli, who's a PhD student under my supervision in Rome, and is responsible for the numerical simulations that I'm gonna show. Marina De Amicis, who was a master's student in Rome, and she recently moved to Copenhagen for the PhD. And Taishi Ikeda, who's a postdoc in my group in Rome. Yeah, I'll be discussing what is the fate of Hawking evaporation in gravity theories with higher curvature terms. And as you can see, there is a question mark in the title, because I will probably provide more questions than answers in my talk, but hopefully in the process, we will also discover something which I found interesting. So there are several motivations for these studies. Let me try to put everything together. They come from different directions. So one of the main motivation is that, well, we have learned yesterday that we tested gravity and we are testing gravity in the strong field regime, finally, both with gravitational waves, with the images of black holes, and this is great. And gravity GR has passed all these tests with flying colors. However, if you look at the regimes that we have probed, which we can divide in this two-dimensional space, one is the gravitational potential and the other is the curvature, it turns out that we have probed regimes when the gravitational potential is of order unity, so very close to the event horizon. And on the other hand, there is the curvature scale there that we have probed in regimes which are orders of magnitude better than, for example, in the solar system. But this is completely off, of course, the Planck scale or any quantum gravity scale. So it's high curvature in a sense, but very low compared to what we expect at the Planck scale. And in order to improve on this, because the curvature goes like 1/r squared, we either need to go inside the horizon or consider microscopic black holes. We need to go inside the horizon because the horizon is a natural cutoff of your theory. You cannot really probe the interior unless, well, as is the topic of this conference, there is no horizon. And so we have access, in a sense, to the interior of the object, and then we can probe this region here with gravitational potential bigger than unity and potentially also higher curvature. But my point here is that there is an entire region, actually a very large one, these are orders of magnitude difference in the vertical scale, in which what I could call the curvature frontier, there is essentially no test of gravity for that high curvature. And this might be relevant for microscopic black holes or anyway in the early universe when such high curvature regions can appear. So these blue lines are where we tested gravity. The others is where instead we don't have any strong tests so far. The second motivation, which is related, of course, is how do we test this high curvature region? And there is a very standard process that we know. It's a semi-classical effect, which is Hawking evaporation. Because Hawking evaporation, what it does is to take a black hole, the black hole radiates, so shrinks and reduces its mass, but increases in curvature. So even if we start with a black hole that in principle has low curvature, during the process of Hawking evaporation, the curvature becomes larger and larger. And therefore, this is a process in which it is inevitable for higher order curvature terms to become relevant at some point during the evaporation. Of course, we know in GR, things break down at the Planck scale. So we don't trust the Hawking evaporation anymore when we approach that scale, but it might be different in other theories. Maybe there can be some cutoff that stops Hawking evaporation, produces remnants, for example. And this is something we want to understand, even though we need a theory and we don't have it so far. So I'll be referring to this formula that I wrote there. This is the mass loss of a black hole due to Hawking evaporation. G is the gray body factor that I will discuss later. T, of course, is the Hawking temperature, and this formula just tells you that a black hole reduces its mass during the process of Hawking evaporation. As I was saying, this might have implication in the early universe and also for primordial black holes. Just one example, primordial black holes could be the entirety of the dark matter if they are sufficiently light. The problem is that there are bounds on primordial black holes in dark matter with masses smaller than, say, 10 to 15 grams, coming from the fact that they should be completely evaporated by the current epoch. Of course, if there are remnants, those bounds are completely relaxed. And then there is another motivation, which is the fact that if you want to modify gravity with higher curvature terms, then you can start with the Einstein-Hilbert action. So there is the Lagrangian. And then you add an extra term schematically in this form with higher curvature correction. So for example, an R-squared term, then inevitably you will have a new length scale. So with some dimension. And the question then is, when I reach that length scale, and this is inevitable again during Hawking evaporation, what happens to black holes with that size? So there is clearly a new length scale in the problem, which might be Planckian, but might actually not be Planckian because it might be in all that region over there that is not constrained by experiments, in which we don't really know what is the fate of black hole evaporation. Okay. And I'll use this theory as a test bed, and I will explain you why. Because of course, in order to study this problem, we need a UV completion of GR, or anyway, we need a theory that works at those scales. One might argue that we don't know this UV completion, or even if you have your favorite one, it might be too complicated, too involved to do simulations. And in fact, here what I want to show is the non-perturbative dynamics of a given theory in that regime. So it's very important not only to have vague ideas of what is the end state of the Hawking operation, but really to have a working theory that I can use and crank and try to understand whether, what happens there. And this is my test bed. So is what is typically called Einstein-Scar Gauss-Bonnet gravity. I'll call it EdGB, where D stands for dilaton. And the theory is the following. Is Einstein-Hilbert action a scalar field, the dilaton, coupled to the Gauss-Bonnet invariant with a coupling function that, for the purpose of this talk, I will take to be exponential. And this is why it's called EdGB, so dilatonic coupling. And this theory is inspired by heterotic and bosonic string theories. In fact, I think it's a consistent truncation in spherical symmetry, at least, of bosonic string theory. And it... Sure. The strength is fixed. Yeah. I will use it fixed also. Yeah, I will fix it.
In that case, this term appears near the cutoff scale of the theory. So using it to solve classical equation is. I understand that you're doing a phenomenology, but I just wanted to stress that the connection to string theory is not there.
I agree. It's also related with something that I was about to mention, that of course I will take this as an exact theory without any of course this is an expansion in the string tension, right? So I'm neglecting all higher order terms, which is precisely your point here. But why do I want to do that? Because this is the only quadratic gravity theory with second order field equations. And that for me is very important, because if I don't do that, either I consider the theory as an effective field theory, and you can do that, but then you find boring physics, I would say, or you end up with something which is not second order field equations, and theories like that are problematic. They are plagued by instabilities. There is a theorem due to Ostrograssi that tells you that if there are higher order field equations, most likely your theory is pathological. So this is why I want to use this theory. It's the only quadratic gravity theory with second order field equation. And this is very important because I can take this theory as exact, of course, from a phenomenological point of view, not from a string theory point of view, and really study it in details. And this coupling lambda here is just by dimensional argument related with the fundamental length scale that I was mentioning before. So L is proportional to the square root of lambda. And let me stress that it's not necessarily Planckian. So I will not take this to be the Planck length because I don't want to mess up with quantum gravity effects. And yeah, you might have concerns similar to what Rami mentioned before, and they will be very motivated. Let me just mention that and stress that I think we should also a bit broader the perspective to avoid doing like the drunk person of this cartoon that is looking for his or her keys just under the light of the lamp. And of course, here the lamp is lighting stationary solutions, perturbation, linear theories, multiple moments, quasi-nova modes, things that we control, we all know how to compute. But maybe they are, I mean, there is something else outside our light cone, so to speak. And the key here is really doing non-perturbative dynamics. So studying the non-perturbative dynamics beyond GR. And this is why I'm considering this theory. Okay, so let me focus now on this and study black holes in this theory. So the equation of motion at classical level are this one. Here there is a complicated stress energy tensor, then there is a scalar equation here. And even without entering the details, you can see the main ingredients of the theory already at this level. Because say, if you take a Schwarzschild black hole, the Gauss-Bonnet invariant is non-zero. It will always be non-zero essentially for a black hole, which means that the right-hand side of this equation, unless f prime of 0 is 0, is different from 0. So we will source a scalar field. So this already already tells you that black holes in this theory have a non-trivial scalar hair around them, which is of second kind. This means that the dilaton charge is not a free parameter, is proportional to the mass. So there is a one parameter family of black holes in this theory. And the properties of these black holes depends quite a lot on the coupling functions. And again, focusing on this form here, there are two cases. One is when this gamma is sufficiently small, meaning that the nonlinearities are not that important. In this case, there is a single branch of solutions that I'm showing here an example of this blue line here. So this diagram is radius of the black hole versus its mass. For GR, this will be a straight line, r equal to 2m. In this theory, it's not exactly a straight line. For big masses, meaning small curvature, it is, of course, it corresponds to the GR limit. Otherwise, it gets a bit deformed, but it's very similar to GR. In fact, what happens in these black holes is that there is a singularity inside the horizon, just like Schwarzschild. And what happens is that the smaller the black hole, the closer is the singularity to the horizon, so it's moving outwards in the space of solutions until you reach this point here, the minimum mass black hole in this branch, which is singular. So the horizon is singular because the curvature singularity has just hit the horizon for that particular solution. However, if you take a bigger gamma, and in particular there is a critical value very close to 1.3 here, something weird happens. So there are two branches of solutions. The minimum mass, like I'm showing here in this green line, or also this orange line is the same. The minimum mass is not anymore singular, it's actually perfectly regular. There is a second branch of solution that separates two branches, a stable one, the upper, and an unstable one, the lower. I will show you why these are stable and unstable. And yeah, as I said, the minimum mass is regular. There is also a minimum radius solution, which is also regular if gamma is large enough. And then in all these branches, the last point of the second branch is again singular because the singularity becomes naked in a sense, okay? But for what matters in my talk, it's important that the minimum mass solution is regular, is marginally stable because it's actually at the border between this stable and unstable branch. And the critical mass scales, as you might expect, with square root of lambda, so with the fundamental length scale of the theory. And again, this is a non-perturbative effect. If you treat the theory as an effective field theory, you will never see this effect because it appears non-perturbative. Then you can study something else in this theory, which is the temperature and the great body factor. And this, in fact, was part of Marina Zdamici's thesis last year. So if you compute the temperature as a function of the mass, you see what you expect. So at large masses, you get the GR results. This line is the GR results. When you approach the minimum mass solution, the temperature is slightly higher, but is in fact very similar to GR. But the crucial point is that the temperature at the minimum mass is non-zero. And same thing for the gray body factor. So the gray body factor here, you cannot see the difference, is the gray body factor at the minimum mass compared to the gray body factor of a GR black hole, and they are essentially almost the same for scalar and vector perturbations. The reason why they are the same is because the gray body factor depends on the photon sphere, essentially. So the curvature of the photon sphere is already smaller than that of the horizon. So this theory is already very good, very well approximated by general relativity. So the gray body factor is similar, the temperature is slightly higher. What happens if you plug this into this formula is that at the minimum mass, there is a mass loss, which is in fact very similar to GR, in fact a bit larger, 10% larger than in GR. And now you see where I'm going. We have a puzzle here. And the puzzle here, what happens to black holes when they start evaporating? Because I can take this Gedanken experiment. I start with a black hole, which is sufficiently massive, so low curvature, GR is a good approximation. It starts emitting Hawking radiation on this branch. It becomes smaller and smaller. Also, the radiation starts growing because the temperature becomes hotter and hotter. Eventually, it reaches the minimum mass solution. The minimum mass is regular, so there is no singularity there, but also there is no lower mass black hole this solution can go to because there is a minimum mass. So the puzzle is what happens to this solution when it should radiate even more. And let me stress that this is very different from general relativity, because in general relativity, the same would happen, but you will reach the Planck scale and then you invoke quantum gravity to solve this problem. I can take the fundamental length scale of this theory to be much bigger than Planckian, and I should be able to resolve this problem without invoking any quantum gravity effect. But of course, this is a puzzle. Let me also put another piece of the puzzle, that the phase space of solutions in this theory, even in spherical symmetry, is actually pretty rich. There are not only black holes, there are also other horizonless solutions. In particular, the two-dimensional space, this is lambda divided by m squared, and this is the dilaton charge divided by m. So these are dimensionless numbers. This branch here is the black hole branch. So it's a one-parameter family of solution. As I was mentioning, this is secondary hair. So for a given dilaton charge, you just have a single mass. Here is a zoom in, and you see that there is a maximum nearby here, which corresponds to the minimum mass solution. This branch here is what corresponds to the second unstable branch of black holes, and this point is the singular black hole solution. What happens is that while the black hole family is a one-parameter family, there is a two-parameter family, so an entire regions of solutions, which are actually wormholes in these theories, and they have a throat at R naught. So these are curves at constant lambda divided by R naught squared. And interesting enough, they connect these points here to the corresponding black hole solution on these lines here. So each black hole solution is actually a double point in the phase space. When a black hole and a wormhole coexist, the wormhole has matter at the throat, but in this theory, the matter does not need to be exotic. So it does not need to violate any energy condition because it's modified gravity. There are also other solutions. These one are called cusps, and they have a singular, so the second derivative, radial derivative of the scalar field diverges. So they are not very physical, I would say. And in fact, they connect to the singular black hole solution at in the second branch. And anyway, they exist in this regional parameter space here. There are also other solutions that I'm not showing here. But the crucial point is that the minimum mass is also a double point when there is a wormhole with the same dilaton charge and mass. Okay, so this was to set the stage and why I think this problem is interesting. And what we then try to do, and well, it took us a lot of time, was to set up nonlinear simulations in this theory, fully non-perturbative. So there are no approximation here. And this is what I'm going to discuss next. So conceptually, the problem is simple. You take your field equations. They are very complicated in general. You take a spherical symmetric ansatz, and because we want to look at what is happening inside the horizon, we use horizon penetrating coordinates, something similar to the standard Painleve Goldstrand coordinates. This is the ansatz for the metric alpha zeta are function of t and r. Then there is an aerial coordinate which we use arbitrarily. We fix arbitrarily in order to have higher resolution in the high curvature regions. Sorry. We have some auxiliary variable for the scalar field and for its momentum. You plug these ansatz into the modified gravity equations, and what you get are 7 PDEs in time and so in t and r. So it's a 1 + 1 problem plus 2 constraints. And then you want to solve all of these consistently. Of course, there are a lot of numerical details that I'm not going to discuss related with the radial grid, the initial conditions, the dissipation terms that you should put in order for the simulation to be regular. But anyway, if you want, we can discuss it later. Let me just mention that this is something that has been done in the past, also in these papers here, and it works pretty well, and it can be done very accurately. Okay, before showing you the simulations, let me also mention some other things. So I already mentioned that there is a singularity for the stationary solution inside the horizon, just like in Schwarzschild. However, the location of the singularity at the minimum mass depends on the coupling constant of the theory. So again, focusing on the same coupling constant, depending on gamma here, the singularity, which is this red curve, can be very close to the horizon. So the horizon here in this unit is at 2, and this is the location of the singularity. So this means that you don't really want to use gamma too small, because otherwise you will need a lot of resolution in order to avoid the singularity messing up with your simulation. So what we did eventually was to take gamma = 4, just because, as you can see, there is a neat distinction between the singularity and the horizon, and this is better for numerical purposes. This case is gamma = 4, the one that I will focus on, and as a function of lambda, which means for different black hole masses, you see that the singularity is always inside the horizon here, and then eventually, so this is the minimum mass solution, and eventually it reaches the horizon at the singular solution that I was mentioning before. But we don't care about this because we will focus essentially on this stable branch. But as you can see, there is something else here. Not only the singularity, there is what I call the excision boundary. And this is something that instead you don't get in GR. So what happens is that in this theory, your field equations, at least in this formulation that we are using and everybody uses, are not always hyperbolic. So it means that the system of equations can lose hyperbolicity. And more technically, what happens is that if you compute the principal symbol, so these are the equation, your field equations, VI are the variables, and this is a standard definition of the principal symbol of your PDE system. You can compute the determinant. When the determinant is 0, you get the characteristic velocities that essentially tells you how fast are the sort of perturbations along the different direction of your space-time moving. And these are the characteristic velocity in a schematic form for this theory. This delta, of course, is a function of the variables. Rami, you have a question? Absolutely.
Curvature. And I would say now, even in some background, you don't get them, you get it in another background. So in a sense, that makes the theory less attractive. You wouldn't really call it a modified gravity. I understand that this is a way for parameterizing deviations from GR. I understand that, but as a theory of modified gravity, because of this problem, which is generic, I would say that
I partially agree with this. I would not call it generic because actually there is no theorem that proves that there is no other formulation in which this principal symbol.
Actually, Paolo, I worked on this also, Harry Real, and there are lots of discussion about that, and it's very clear that
I don't think so. I mean,
okay, we can
discuss it later.
But my perspective is that this is happening everywhere.
I mean, if one takes your perspective, I think we can study this as a model, as you said. But honestly, I think that the proofs that are around are a bit. I mean, they're limited under certain hypotheses. We can discuss it later.
Okay.
But, yeah.
Okay, thanks.
There is also this paper by Ripley and Pretorius in which they show that loss of hyperbolicity is generic if you use point transformations, which is not the most general foliation that you can use. But anyway, yeah, okay, let's discuss it later. So in bosonic is square root of 2 in these units. So it's already bigger than the critical value. So it's already essentially when the minimum mass is regular. In the other case, it's gamma equal 1. So in that case, the minimum mass is singular.
Okay, thank you.
Yeah, let me just mention that we were discussing already with Rami. In GR, this does not happen because the characteristic velocities are real. So the loss of hyperbolicity is related with the fact that the characteristic velocity becomes imaginary. And this happens when this determinant becomes negative. And so what happens is that in this theory, depending on the background and your simulations, it can happen that you have these problems. And here is where you have these problems. So just outside the singularity, but within the horizon. So one might actually even argue, well, actually, I'm not sure that this is totally physical, but even if it is physical, physical means that it's not a gauge effect. Even if it is physical, one might still be happy with this as soon as it remains within the horizon, just like the singularity. I mean, the singularity, of course, is a problem, but we don't care too much because it's inside the horizon. The same can happen for the elliptic region, but I will show you that it's more problematic here for, well, for reasons that we'll see. Okay, so let me now do 3 Gedanken experiments. So now I will show you these simulations here. The first one is very simple. We take a black hole in the upper branch, so which is stable, and we add a tiny dilatonic perturbation on top of it as initial data. So we solve the initial data exactly numerically, and these are our initial data, and then we solve the initial value problem in this theory. So because we are adding a small perturbation, this is adding mass to the space-time. This MMS is the Meissner-Sharp mass. And so we start with this black hole here. We add a small perturbation. So in fact, we are starting at this precise point here, and then we let the perturbation evolve. What happens is what you expect. The black hole absorbs the small dilatonic perturbations. It grows in mass, and it settles down toward a new stationary solution with a slightly larger mass and slightly larger radius, exactly as you would expect. Let me see if I can show you the simulation, but anyway, it's very trivial and it just says what I have described for you. So now you will see a zoom in of your parameter space. This is important because we are looking really at tiny perturbations here. So instead of having this expanded branch, you will see something much smaller. And then you see here, we start with this initial data, we add a small perturbation. And from here, this is just an animation, but from here is really the simulation that what does is to increase the radius at fixed mass because the mass is invariant, right? So the total mass of the space-time does not change. So the thing that these things does is just going up toward the stationary solution. Okay. Second Gedanken experiment, we instead of starting from the upper branch, we start from the lower branch, which is supposedly unstable, and we can prove it is in fact nonlinearly unstable. So what you can do is start with any of these points here, add a small perturbation, just like before, and it can be arbitrarily small, it doesn't matter, because this solution, this branch is unstable. So the moment you add a perturbation, the solution will migrate from here to the stable branch, just like, for example, if you are familiar, a neutron star will do in the unstable branch for small perturbations. And what I'm showing here is how the radius of the horizon evolves in time. Initially, it absorbs the dilaton perturbation, but after that, because the solution is unstable, it migrates, so the horizon grows to reach this upper branch. Of course, the time scale for this depends a bit on when you are, because the closer you are to the minimum mass, the longer the time scale, because here the minimum mass is marginally stable, okay? And again, here I have a simulation for this, but I think that you already understood how it goes on, so I will skip this. And now it comes the interesting part. So all of this was to motivate this plot that took us a lot of time to do. Now I want to do the same, but I want to mimic Hawking radiation, so mass loss. And if you think about it, we thought a lot. It's very hard to mimic mass loss by classical processes. So you want the black hole to absorb some perturbation, but reduce its mass instead of growing it. And well, as you know, there are also theorems in GRs that tells you that the area of the horizon cannot shrink. So how this can happen? So the simplest way we found to mimic this process, of course, we don't want to mess with semi-classical effects, is to use a phantom field. So a ghost with the opposite sign of the kinetic term in the action. So what this ghost does, this is not part of the theory, it's really part of the matter sector, okay? So what we are doing is throwing a black hole, starting with a black hole in the upper branch, in the stable branch, and throwing a ghost field, a tiny one, that just reduces the mass of the black hole a bit upon absorption, okay? And well, we made a lot of tests to make sure that this made sense, and in fact it does. If you do it in GR, you start with Varshig, you throw a ghost field, what happens is that you end up with Varshig with a smaller mass, little smaller mass, and of course, smaller radius. And this is what is shown here. So we start with this, we include a ghost field, so the mass now goes in the other direction. You make the simulation evolve, and you end up on the stable branch. And this happens all the way down for all these solutions. Now you see where I'm going. If we start with these guys, which is very close to the minimum mass, and we throw a ghost field, even if the amplitude is tiny, the mass of the initial data is smaller than the critical mass, the minimum mass black hole solution here. So the question is, what happens to this guy when we evolve the simulation? And because this is important, let me now show you what I'm talking about. It should be clear in this plot. Why it's not working? Okay, because it's already open. Wait, let me start again. So now we are on the stable branch, all these solutions here. We add a phantom field. We start now the simulation, and they just reach stationary configuration. But if we start with this guy here, we add a phantom field, and then we start now the simulation. This guy starts decreasing his horizon, decreasing. Of course, it does not intersect this line here. And then the simulation keeps going, in fact, for a long time. And now I'll show you what happens. Something interesting. Wait, no, it's not this. It's this. All right. So the first thing that we saw is that you see initially, the dynamics is very mild. So this is the horizon. Originally is at 2. It decreases, but very little, just like it would do in GR by absorbing the ghost. And it absorbs the ghost, this is important, around here. So at around 15, okay? Because the ghost is very close to the horizon. So the rest of the dynamics is not due to the ghost. It's really due to the theory that does not know where to go in that parameter space. What happens is that at much later times, and actually this is very challenging from the numerical point of view, is 2000 unit times, the horizon shrinks eventually more dramatically, but also the excision is growing. So the elliptic region, which is within the horizon, is moving outwards, and eventually at this point it's hitting the horizon. This, of course, as Rami was saying, dramatic for the theory, because an elliptic region is appearing outside the horizon, and of course cast problems on the, I mean, we cannot follow the evolution any further because the problem is not hyperbolic anymore. And in fact, this is an important point to keep in mind. Excision means that you are really removing the space-time for smaller radii, which means that we don't have control of the simulation within the excision region. Okay. So in particular, we know that at t equals 0, there is a curvature singularity here. We don't know how this singularity evolves, but we can have some intuitions by looking at this plot. So this is a very important plot. Is the space-time diagram, time radius of the curvature invariant. So these are a gauge invariant during the simulation. So this is t equals 0, and this is time. and these are just zoom in version of the same plot. So as you can see from the scale, this goes from 0. This goes only from the very latest stage up to the point when the horizon crosses the excision. And these are even the farther later stages. What I'm showing here in colors is the curvature normalized by the curvature at the horizon at t equals 0. So we start with a black hole, which has some curvature at the horizon. It is typically small. So whenever you see the curvature being 100 times bigger, it means that in the red regions, the curvature is 100 times bigger than the curvature at the horizon of the original black hole. Okay. This white curve is the apparent horizon, which is shrinking, as we already know, and the black is the excision region, which is growing. Okay, so there are two take-home messages here. Actually, yeah, 2 or 3. So one is, okay, the apparent horizon is shrinking and is probing regions of higher curvatures. This is almost obvious because if the horizon shrinks, the curvature goes like 1 over r squared, so it should be larger. What is more important is that even at fixed r, the curvature in time is growing. So if you take an r equal constant section, the curvature is growing in time. And in fact, if you look at the level curves, they are tracking the excision region. So our interpretation here is that the curvature singularity, which is inside the excision, is actually moving outwards together with the excision boundary. And in fact, the curvature, you see, of the space-time is really following this trajectory. So our interpretation is that behind this red, just across the excision region, there is a curvature singularity that is moving outwards together with the elliptic region. And it does so until this point here, when the horizon touches the excision and most likely is very close also to the singularity inside it. So this is point in some sense toward a naked singularity formation in this theory in a dynamical way, because you see the curvature is growing by a lot. And if we increase resolution, we keep following the simulation for longer and the curvature grows even more. Of course, we cannot claim that there is a naked singularity formation because the singularity is within the excision, but for sure, well, for sure it's a big word, but most likely there is an elliptic region, a naked elliptic region, meaning that the elliptic region wants to go outside the horizon. And this, in this particular theory, has been seen also in other cases, of course, not for the mass loss that is explored here. Rami, you have a question? No. Ah, sorry. No, I'm about to done, then we can discuss. An important point here that took us some time to be convinced about is what happens in the very last stages of the simulation, whether we trust it or not. And here I'm showing almost the last time snapshot and the curvature, the radial profile of the curvature. So as you can see, compare this to this, it changes only by 4 time units, and the curvature goes from 40 to 150. So this already tells you that it's growing a lot. Not only that, these are different numerical resolutions. As you can see, the lowest resolution did not converge, but here you cannot tell the difference. There are two curves, one black, one blue, and one red. They are on top of each other. So we trust our code up to this time here, where already the curvature is growing a lot. So I think that it's physical that this is growing that much. We don't know, of course, what happens after the horizon crosses this boundary, because we cannot follow the evolution anymore. But, well, it's interesting that this is happening. An important point, this is probably my next to last slide, is the fact that I was talking about apparent horizon. So apparent horizon in dynamical situations, that does not mean much. Because it's foliation dependent. There might be cases in which there is no apparent horizon. In GR, we know there are theorems that rely on the energy condition that tells you that if there is an apparent horizon, it must be enclosed by an event horizon. And this is very convenient, because then you look for an apparent horizon and you are sure that there is an event horizon in your spacetimes. The two constants coincide only for stationary solutions. But in this theory, so this theory violates some energy condition at the modified gravity level. So there is no reason to expect that the apparent horizon is always within the event horizon. And in fact, we have computed the event horizon just by doing null ray tracing, the same thing that Sam Gralla explained yesterday on Daniel, talking about the event horizon telescope results. So what we did was to trace back in time null geodesics and look at the region when they converge and back in time, and their surface when they converge is the event horizon. And as you can see here, the event horizon in this particular case, so just before the simulation crashes, is within the apparent horizon. This is the first funny fact. The second fact is that the event horizon is tracking the apparent horizon and is actually moving inward, so it's shrinking. This is something that will not happen in GR. We know that in GR, the event horizon cannot shrink. In this case, it's shrinking because the dynamics of the theory is different and is moving toward higher curvature regions. So again, this is pointing to the fact that there is a higher curvature region emerging out of the event horizon. Then we don't know the end state, unfortunately, but this is the situation. Let me just mention this is not always the case. If your simulation is less dynamical, like in this case here, this is the same simulation, but earlier in time, what you see is that the null geodesic converges toward the apparent horizon. So in this case, the apparent horizon and the event horizon are almost the same because the dynamics of the theory is very mild. And finally, there are also other cases. This is a transition from unstable to stable in which the event horizon is outside the apparent horizon, as you would expect in general relativity. Okay, so conclusions. So I think that this is a nice example of what numerical relativity can do for theoretical physics. So there is a lot of effort now to use numerical relativity to compute waveforms, gravitational waveforms, to do tests of general relativity with LIGO and Virgo. However, it can also be used on a more theoretical level to devise Gedanken experiment studying the full non-perturbative dynamic of a theory beyond GR, and this is what this project was about and is about. I would claim that Hawking evaporation in this theory is bound either to violate the weak cosmic censorship because it will form a naked singularity or anyway a pathological region outside the horizon, or to produce an horizonless remnant. Why am I saying this? Because as I was showing before, the minimum mass solution is a double point in the phase space. There are other solutions which are horizonless. So a possibility that, of course, we cannot prove at the moment is that the black hole migrates, so transit toward a solution which is horizonless and, of course, does not radiate anymore, and it will be stable. The problem with this, and I guess this is intimately related with the hyperbolicity and the problem that we encounter at the end of the simulation, is that your space-time has to change topology, because we start with something that has an horizon and eventually the horizon should disappear. I think, but actually, this is really just an expectation, our current numerical methods are not good enough to deal with this, but we should think about it. And anyway, an important point is that the fate of this problem, I mean, this is a puzzle, it's still open problem. The fate of this should be addressable without invoking quantum gravity, which I think is important. And it will have consequences for primordial black holes in dark matter if remnants, horizonless remnants exist. Maybe for the information loss paradox that, of course, is of interest here. Of course, one might argue there is not enough freedom or ways to store information within these remnants. But I mean, still, I think it would be interesting to find an example of a dynamical formation of an horizon-less remnant in a given theory, starting from a classical black hole. And these are, well, things for the futures. These are intimately a non-perturbative effect. So an important point is to understand how generic this is, because it can be broken in several ways. For example, by higher order terms that one can add to the theory, or by other theories. Of course, I just selected one because of good motivations, but I would expect that something similar, at least in principle, should work for higher curvature corrections different from this particular theory. And then there is this issue that I will leave as an open question, is related with also what Rami was pointing out. I'm not totally convinced that the loss of hyperbolicity in this theory is physical, at least not as generic as it might seem. It might actually be a gauge issue in my perspective, or anyway, I don't have a solid proof to say that the formulation that we used is generic and there is no other formulation in which this problem of loss of hyperbolicity does not occur, which would be very important because we want to run the simulation and understand what happens even after the horizon crosses the elliptic boundary. So it would be very important, for example, to even have another formulation in which there is an elliptic region, but maybe is more confined within the horizon than in this case here. There are examples, there was a paper a few days ago trying to avoid these issues, and I mean, there is a lot of progress there, and I think something interesting will appear soon. Okay, so I'm done. I thank you for the attention, and I'm happy to take questions.
You mentioned the divergence of the scalar field, the center point. Can you correspond to some extra dimension in hydraulic string, for instance, is expected to be 11-dimensional when the dilaton is a strong coupling?
It might, yeah, I mean, it might be. Here, really, we are looking at the theory from a 4-dimensional point of view. Only some of these solutions are singular. So in particular, in this branch here, the only singularity that exists is in the second radial derivative of the scalar field that diverges. And then there is this particle-like solution that we're studying in this paper by Kleinhaus, Kantz, and Canti. They did actually a lot of work in this theory from the static point of view. And well, I didn't write it here, but there is a 2-parameter families here in this region that connects to these caps. And they are also singular from the scalar field point of view. So yeah, it might actually be a sort of reminiscence of that.
I have a second question, which is related to causality violation. So typically, when you have gravity and you add the R square, R cube term, you violate causality, especially when you take this parameter to be not a Planck scale, but much larger. So I don't know whether the dilaton can help a little bit.
So you are referring to Stell. Yeah, it's not a Tachyon or a ghost. So it's not Stell. It's not like Stell theory. You see. So in this theory, so the thing you are talking about causality is related with this problem here. That typically you have higher order field equations that comes with a lot of problems, and you can treat them only perturbatively. So if you sort of integrate out the high energy degrees of freedom, here you don't have this problem. So in principle, the equations are fine, but you might have problems with the. You no longer can involve your equation. Yeah, well, I would call. Yeah, I mean, I would call laws of causality the fact that the velocity is higher than the speed of light, which is not the case here. Is loss of the hyperbolicity, in fact, meaning that if you know the solution at a given time slice t, you don't know how to evolve at t plus delta t, which is actually probably more problematic than loss of causality. It's probably even worse, I would say, because I can accept things going superluminal, maybe. Wow, almost.
Popular time crystal stuff is the same thing, has the same problems, and it's actually a singularity right? Because you evolve the equation and you reach a point where you can no longer evolve them. So this is the essence of having a singularity in the theory. The GR singularity are the same. You just cannot evolve the equations anymore.
Yeah, I think it's a bit conceptually. I see your point, and I think I agree. I think it is a bit different because I mean, singularity means the curvature is diverging.
No. In the singularity theorems, the definition of it.
Theorem, sorry.
Well, that is the singularity in GR, right? The singularity theorem tells you that you cannot evolve the equations anymore, any further. But they don't say anything about the size of the curvature.
but in GR there are not elliptic regions, right? I mean, the formulation is there is no. I mean, GR is strongly hyperbolic, right?
Yes,
So
yes,
it's a
but
different
what I'm
problem.
saying is that in conceptually, this
Oh, yeah,
and
this is-
singularities are the
I
same.
agree. But yeah, but I would say, I think that conceptually are different because one is a breaking of the curvature, which is sort of physical. The other one is the formulation, right? But I mean, I agree that having this problem, like in this case, is equally as bad as having a singularity.
Very different question. Within couples, breaking couples, and so forth, generally have a lot of experience. So I want to get a sense of what you're doing these kinds of numerical simulations for the complex one. What's the sort of limit on it's presumably functions usually function two variables and roughly how many fields
You cope with reasonably in this sort of situation.
So is it a question? Let me try to repeat. Is it a question whether something similar could be done in a fuzzball?
Yes, but also, you know, I want to get a sense of how many degrees of freedom you can activate, because fuzzballs generally come with a lot of degrees of freedom.
Yeah.
So what is viable in this kind of simulation?
Yeah. So I think as long as the yeah, I mean, of course, this is something on the back of my mind, but so I would say if you take low energy theory describing the fuzzball, so say supergravity theory with a given number of degrees of freedom, you can treat the evolution for gauge fields, scalar fields coupled to gravity. No problem with that. Of course, it's technically challenging, but you can do it. My sort of problem that I think is something, well, maybe it's for tomorrow's discussion session, but if you take that particular theory, which is essentially in the Einstein frame GR with all these fields which are coupled to each other, right? In that case, black holes are a solution of the theory, right? So for example, if I take a fuzzball, or even if I can take two fuzzballs, I'm pretty sure, of course, one should prove it, that if you make the merger of two fuzzballs, you form a black hole, just because it's part of the parameter space of your theory. Then you will say, wait, let me finish the argument. Then you will say, before forming, I mean, I'm talking about classical level, right? Because I can only evolve classical equations. Then you will say, before forming the horizon, something, I mean, the description breaks down, I should include more ingredients, and I think I agree with that. The problem is that I don't know how to model it properly, right? But if I take the classical equation, so really supergravity, I'm pretty sure that what happens is that it will form a black hole. It depends on the initial data. You might actually form also something else, but it's conceptually very similar to, it's actually very similar to this, in fact. There is no really way the theory knows that you should not form a black hole.
I think when you have extra degrees of freedom, they can actually stop you from forming the black hole. And in particular, so normally, okay, in some systems which are simple, the extremal systems, you know, when you collapse a bunch of branes, of course, you know, you put them together, you collapse them, and they're going to form a black hole. But when you have a fuzzball, you also have magnetic sources and electric sources. And when you have electric and magnetic sources coming together, they actually repel each other. So for example, the 0 and the 6 branes, which are electric and magnetic dual, they repel each other. So when you have a fuzzball made of some objects which has some charge, but the ingredients are actually the 0 d6 centers, and the other one has also some 0 d6 centers. When they join, they will repel each other. So there will be a repulsion. Not if you look at the overall charge, of course, it looks like it's coming together. But if you look at the ingredients are going to repel each other, and they're going to keep the thing large. So that's at least in some examples which are worked out.
Yeah.
But I think what Paolo is saying is this what you're saying is not a supergravity thing, really. Yes. But I mean, if you take some nice, you know, semi-classical fuzzball, right, which we can write down in supergravity, and you perturb it enough, it'll probably collapse into a black hole, unless you invoke that there's a lot of phase space for it to go into. That's not within the supergravity, right? No, I don't think this.
Right.
No, that's the whole point. So for example, if you look at the two-charge system, like, you know, if you take a Lunin Matur super tube, which, and, you know, you can make it figure eight, so the charge is the same as the black hole charge. And then, you know, you bump it with something, and then you say, great, you know, it has, you know, no angular momentum. So, it has mass, it can collapse into the black hole. And then, you look at the full phase space, which is given by some classical phase space. I'm not talking about anything quantum, by some arbitrary functions of like, four variable of like, one variable. There's no way in that phase space with arbitrary functions to reach the black hole point. It's just highly unlikely. You have a function of four you have four functions of one variables. If you just look at the generic space of functions to get the black hole, all the functions have to be zero.
What is the
evolve a random function?
But what is the problem with that?
Sorry?
What is the problem? I mean,
it will not go to the black hole point. It will just go to other configurations.
How do you know?
No. You can make it time. I think we can make it time dependent. It's not a problem.
Yeah. Can I add something? So yeah, we should discuss this because of course it's super interesting, and I'm not saying that I know the answer. This is just my interpretation. But what is different from what you described? Say, if I take two neutron stars, so these are like perfect fluid clumps. Is very complicated in general. So it's a particular solution of the theory. Then I make them merge, and it can happen that they form another neutron star depending on how much energy they have, or they form a black hole. So they collapse to a black hole. And again, you start with something that has a profile, is very complicated. So the pressure has a given profile, and it has to be zero in the black hole, but this is what happens. I can also take another example. If you have a semi-classical theory, for example, take a fuzzball. If you take two fuzzballs and you make them collide with enough kinetic energy, even just by kinetic energy, because kinetic energy gravitates, in a semi-classical theory, this should create an horizon. Really just the kinetic energy. I don't even care they are two fuzzballs. If I take two anything and I make them collide at the speed of light, eventually they will form a common horizon. And in order to avoid that, I think that you really need quantum tunneling or something which is non-perturbative.
So when if you just bound two superficies each other, for example, you just follow this
I think your problem, Joseph, is you're having to invoke far too many degrees of freedom in order to resolve that problem. Okay, but I want to ask a much tamer question. Okay, so one of the things we've been building what we call microstrata. So what we do is we take some supersymmetric, deep scaling solutions, beautifully regular, and we turn on a scalar mode, and that breaks the supersymmetry. We fully backreact it. We see interesting frequency shifts and nonlinearities in those frequency shifts. But the thing we can't do, because we needed this sort of Coleman trick to get it down to single radial equations. But if you put multiple modes in there, just the same perturbations, then there will be all sorts of perhaps interesting frequency shifts. But the thing then becomes time dependent. And the question I guess I want to ask is that within realm of the kind of analysis you're doing?
Yeah, it is.
Okay.
It's technically challenging, but it's
because the interesting thing, what we can see is if you turn on one mode, you can see the frequency shifts and you get bound state energies that are non-linear dependent on amplitudes. Having two or three of them on the go, I would really like to see the transition to chaotic spectra from this.
Well, for example, last year we had this paper with Aishi, Keda, Massimo's group, and others. And where we're considering a test scalar field on the background of these fuzzball geometries, right? Mm-hmm. Of course, the next step there will be not doing a test scalar field, but really perturbing the geometry, and then you will get everything mode couplings and everything is time dependent. In principle, it can be done. It's just that you have to deal with a lot of, but it can be done. Yes.
Okay.